All right, let's jump right into a huge question. What do we do with things we can't get more of? You can think of it like a pie that's never going to get any bigger. How do we decide who gets a slice today versus who might really need one tomorrow? This is a huge puzzle, so let's get into it. Okay, so picture this. Imagine there are only 20 barrels of oil left, and that's it for the entire world forever. How on earth should we use them? Who gets them, and when? This simple question, believe it or not, is at the absolute heart of the entire problem we're unpacking today. So, where do we even begin to answer a question that big? Well, first, we've got to really understand the dilemma we're facing. And as we're about to see, our first, most obvious instinct is almost definitely the wrong way to go. Now, when we talk about non-renewable resources, it's not just that there's a limited supply of oil or coal. The really critical part of this definition is the rate we use it. We are burning through this stuff millions of times faster than nature can possibly make it. So, for all practical purposes, the total amount is fixed. The real challenge is deciding how to spread that fixed amount across all of time. So, what's the simplest solution you could think of? Well, you'd probably just figure out how much oil the world wants today at its current cost, and you'd sell it. And then tomorrow, you just do the same thing all over again. Economists have a name for this. They call it static efficiency. And it's all about making things perfect right now with zero thought for the future. And here is the massive, glaring flaw in that simple idea. Let's say in our little world, people demand 15 barrels in the first period, and then they demand another 15 in the second. Well, that's 30 barrels total. But remember our big problem? We only have 20. So this simple, static, live-for-today approach, it leads to a complete wipeout, leaving the future with absolutely nothing. Okay, so clearly that's not going to work. We need a much smarter way to think about this, a way that actually connects today with tomorrow. And luckily, economists have a really powerful concept for doing exactly that. And that concept is called dynamic efficiency. Now, I know, it sounds a little complicated, but the main idea is actually pretty simple. We need to find the plan that creates the most total value over time. The secret ingredient here is that phrase present value. It's just a fancy way of saying something we all know intuitively. $1 today feels more valuable than $1 a year from now, right? So we have to find a balance that creates the most total good while accounting for that fact. So how do you find that perfect balance? Here's the magic rule. The value you get from using the very last barrel of oil today should be perfectly equal to the value you'd get if you saved it and used it as the last barrel tomorrow. If those two values aren't equal, it means you could shift a barrel from one period to the other and actually create more overall value. That's the sweet spot, the perfect equilibrium we're trying to find. All right, enough with the theory. Let's actually put this to the test. We're going to use our 20 barrels of oil and a super simple model with just 2 periods. You can call them today and tomorrow. Okay, let's try out 2 extreme strategies. First, let's just use most of the oil right now. 15 barrels today, 5 for tomorrow. The total value we get from that is $46. Now, let's try the opposite. Save most of it. We'll use 5 today and 15 tomorrow. That gives us a slightly lower value of $45. And why is that? It's that present value thing again. We just naturally value benefits that happen sooner a little bit more. So using more now seems better, right? But is it the absolute best we can do? Nope, it's not. Neither of those simple strategies is the best path forward. The truly efficient solution, the one that squeezes every last drop of value out of our 20 barrels, is a very precise, very carefully calculated balance. And here it is. The dynamically efficient solution is to use about 10.2 barrels in period 1 and save the other 9.8 or so for period 2. Now, look closely, because there are 2 super important things happening here. First, we still use a little more today, that's that present value effect. And second, look at the price. It goes up in the future. That rising price is a critical signal that the resource is getting more scarce. And that leads us to our next big idea. But hold on a second. Why is the price over $3 in the first place? This question right here brings us to what I think is the most important and, frankly, the most fascinating concept in this entire explainer. So in our model, the actual physical cost to get a barrel of oil out of the ground, the labor, the equipment, all that stuff, is only $2. So why in the world is the market price almost double that? Where is all that extra money coming from? The answer is something called the marginal user cost. And this isn't a cost you can touch or see, like steel or wages. It's an opportunity cost. It represents the future benefits we give up every single time we use a barrel today instead of saving it. It is, quite literally, the price of scarcity itself. So the true price of this stuff really has two parts. You start with the physical cost of getting it out of the ground, are $2. But then you have to add that marginal user cost, that price of scarcity, which in our first period comes out to $1.90. You add them together, and that's how you get the full market price of $3.90. Scarcity isn't just an abstract idea. The market is smart enough to put a very real price tag. Okay, now that we get this hidden cost of scarcity, we can finally zoom out from our simple little example and see how these principles actually shape the future of all non-renewable resources out there in the real world. This all leads us to a big general principle called the hodling rule. And what it predicts is that the price of scarcity itself, that marginal user cost, should rise over time at about the same rate as the interest you'd get from a bank. Now, why would that be? Well, think of it this way. If the value of oil in the ground is going up slower than the interest rate, you just sell all your oil and put the cash in the bank. If it's rising faster, you'd leave it in the ground as an amazing investment. The market naturally finds that perfect balance where it's a toss-up between the two. Now, this rising price can't just go on forever. Eventually, the price of a resource gets so high that it hits what's called a choke price. That's the tipping point where a substitute technology, like, say, solar power for oil, suddenly becomes the cheaper, better option. And this is the really amazing part. The market just naturally switches over. The resource is basically retired, not because we physically ran out of every last drop, but because we innovated our way to a better alternative. So this is a beautiful, elegant economic model. It's really neat. But of course, the real world is always a bit messier. So finally, let's just touch on a few things that complicate this otherwise perfect picture. For one thing, our model assumes a perfectly competitive market. But in reality, you've got cartels that can restrict supply to drive prices up. And then there are massive environmental costs like climate change that aren't included in that simple $2 extraction fee. And, of course, the big one, technology, which can change everything overnight and create substitutes we can't even dream of today. All these things make predicting the exact future price path incredibly difficult, even if the core logic we've talked about still holds true. Which leaves us with a final, really fascinating question to think about. If rising prices are constantly pushing us to innovate and find substitutes, does that effectively make a finite resource infinite? The economic model we've just explored seems to suggest that scarcity itself is the engine that drives innovation forward. The real question for our future is, can our innovation always win its race against